Alright, let's tackle a problem about the commutator of an operator. Here's the question we're looking at. If vector L is the orbital angular momentum operator and vector sigma represents the Pauli matrices, which of the following operators commutes with the dot product of vector sigma and vector L? We have four options listed here which all look somewhat similar. They involve vector L plus or minus some constant times vector sigma. To solve this, let's call the operator we are starting with A. So A is equal to vector sigma dot vector L. Our goal is to find one of these other operators, let's call it X, such that the commutator of A and X is 0. That's what it means for them to commute the commutator, written as a square bracket A comma X is equal to 0. Now if you look at the options, they all have a similar form vector, L plus some constant, let's call it C times vector sigma. So our approach will be to figure out what value this constant C needs to be for the commutator to vanish. We need to calculate the commutator of vector sigma dot vector L with the general form of our option, which is vector L plus C times vector sigma. Using the property that the commutator is linear, we can break this up into two separate commutator terms. It becomes the commutator of vector sigma dot vector L with vector L plus C times the commutator of vector sigma dot vector L with vector sigma. We'll evaluate each of these two commutators separately. Let's take the first term, the commutator of vector sigma dot vector L with vector L. To make it easier, let's look at the jth component of this commutator. So we are evaluating the commutator of the sum over k of sigma k times Lk with L sub j. Remember that the sigma operators act on spin space and the L operators act on spatial coordinates. Because they operate on different spaces, they commute with each other. That means the commutator of sigma k and Lj is 0. Now using the rule for the commutator of a product which is AB, C equals A times B, C plus A, C times B, we can expand the term inside the summation sigma k Lk, Lj equals sigma k times Lk, Lj plus sigma k, Lj times Lk. Since sigma k, Lj is 0, the second term disappears, leaving us with sigma k times Lk, Lj. Next, we use the fundamental commutation relation for angular momentum operators. Lk, Lj is equal to iota h bar epsilon kjl times ll. Epsilon here is the Levi-Civita symbol. Substituting this back into our expression for the jth component, we get the sum over k of sigma k times iota h bar epsilon kjl times ll. We can pull out the constant iota h bar, leaving us with iota h bar times the sum over k and l of epsilon kjl sigma kll. If you look closely at this sum, it's actually the jth component of the cross product of vector sigma and vector L. So the total vector commutator of vector sigma dot vector L with vector L is equal to iota h bar times the cross product of vector sigma and vector L. Now let's evaluate the second term in our original combined commutator, the commutator of vector sigma dot vector L with vector sigma. Again, we'll look at the jth component. This is the commutator of the sum over k of sigma k times Lk with sigma sub j. Using the same commutator product rule as before, sigma k Lk, sigma j equals sigma k times Lk, sigma j plus sigma k, sigma j times Lk. This time, since Lk, sigma j is 0, because they act on different spaces, the first term vanishes, leaving us with sigma k, sigma j times Lk. Now we need the commutation relation for Pauli matrices. Sigma k, sigma j is equal to 2 iota epsilon kjl times sigma l. Substituting this into our jth component calculation, we get the sum over k of 2 iota epsilon kjl L sigma L times Lk. Pulling out the constant 2 iota, we have 2 iota times the sum over k and L of epsilon kjl, L sigma L Lk. This sum is the jth component of the cross product of vector L and vector sigma. So the total vector commutator of vector sigma dot vector L with vector sigma is equal to 2 iota times the cross product of vector L and vector sigma. Now we can substitute the results for the two commutators back into our original expression for the total commutator. The commutator of vector sigma dot vector L with vector L plus C times vector sigma is equal to iota h bar times vector sigma cross vector L plus C times 2 iota times vector L cross vector sigma. We can use the property that reversing the order of a cross product changes its sign. So vector L cross vector sigma is equal to minus vector sigma cross vector L. Substituting this, our expression becomes iota h bar times vector sigma cross vector L minus 2 iota c times vector sigma cross vector L. Finally, we can factor out the common term vector sigma cross vector L. This gives us iota h bar minus 2 iota sigma cross vector L. For the total commutator to be 0, this entire expression must be 0. Since vector sigma cross vector L is generally not 0, the term in the parentheses the coefficient must be 0. So we set iota h bar minus 2 iota c equal to 0. This means iota h bar is equal to 2 iota c. We can divide both sides by 2 iota to solve for cc equals iota h bar divided by 2 iota. The iotas cancel out, leaving c equal to h bar over 2. So the operator that commutes with vector sigma dot vector L is of the form vector L plus c times vector sigma, where c is h bar over 2. This means the operator is vector L plus h bar over 2 times vector sigma. Let's quickly look at our options again. 1 vector L minus h bar over 2 times vector sigma. 2 vector L plus h bar over 2 times vector sigma. 3 vector L plus h bar times vector sigma. 4 vector L minus h bar times vector sigma. Comparing our result, vector L plus h bar over 2 times vector sigma, with the given options we see that it matches option number 2. Therefore, the correct option is 2.